invariant requiring Michael Teper. This is the second presentation on topological aspects. So Mike, thanks for accepting the invitation, and please, the stage is yours.
Okay, thank you very much. Thank you very much for the invitation. I regret not being physically present. I've had many visits to the ECT workshops in past years, and it was always a very useful and enjoyable experience. So I'm just for myself, I'm missing out on that. I was not quite sure what to cover because topology is a very large subject, and there are areas that I have completely missed in this talk. Fortunately, some of them have been covered in yesterday's talk. So, for example, I am not saying anything about finite temperature, non-zero temperature, but Massimo covered that very interesting way in his talk. I'm not saying anything about, well, I'm saying very little about theta vacua, just mentioning it in the context of topological freezing. But that was also discussed both by Massimo and by Constantia Alexandru. And indeed, both speakers talked about fermions, well, especially Constantia talked about fermions, theories with fermions. So I will just talk about topology in pure gauge theories. To the extent that there's some new plots, there are some new plots and so on in this talk. Most of them come from two recent papers with Andreas Athanadorou, which are listed here. And then there was right at the end, I mentioned some new work, some ideas that I put forward in a paper very recently. So this talk is going to be something that, at least for people who are interested in topology, it's probably not too much that is new here, but it's a kind of review. So I will say something about continuum topology, just a brief introductory sketch, then about putting topology from the continuum onto the lattice, calculating topology on the lattice, and then I will talk about the freezing of topology, both as lattice spacing goes to zero at fixed number of colors, and as you let the number of colors go to infinity. And then finally, if I have time, I'll say something about some further methods for calculating the topological charge density. So brief sketch of continuum topology, you're all, I think, familiar with this. If we are in a finite volume with periodic boundary conditions, the gauge field possesses a topological charge, an integer topological charge, which can be written like this. And indeed, as Massimo wrote it, you can also write it as a total derivative of a non-gauge invariant current. Then the minimum action field, if you are on an infinite volume, the minimum action field is the instanton, which in a convenient gauge has this nice form. Here it is, the gauge potential. As you can see, apart from this factor, it's pure gauge. So this factor is only important when x squared is on the order of rho squared, and it becomes 1 at large distances. So the field becomes pure gauge at large distances, and it's not pure gauge within a sort of four-dimensional hypersphere of size radius rho, the core of the instanton. A convenient gauge has this gauge function here having this form, and you can see it's the general SU2 matrix. So, and as you go around the sphere at infinity, in four-dimensional infinity, you go once around the SU2 group. So you're doing a unit winding, and this is the topological aspect of the field. So now this is all in infinite volume. If you want to be in a finite volume, you have to take into account the fact that, of course, this particular solution is not periodic. To get something that's periodic, you can do a gauge transformation, the inverse of this G dagger, use G dagger, apply that to this field, and that makes the pure gauge fields at large distances go to unit matrices. It unwinds that, And instead, you have a little singularity at x equals 0, around which you have to put a ball, and that's where the winding is. So that can be all, this is a pure gauge singularity, so it doesn't affect any of the gauge invariant quantities. In any case, although it could be awkward to deal with because it's a singularity, but on a lattice where we don't have that problem because we can put that point within a hypercube, so it doesn't actually affect any of the field's link matrices that are around the instanton. So at that point, you can actually put it onto a finite volume. Again, a reminder, the instanton action is known to be 8 pi squared over g squared, and the action and the topological charge density are non-zero, essentially within this kind of core, which is on the size scale rho. So this is an SU2 instanton. If you want an SUN instanton, you can take unit n by n matrices, take the top 2 by 2 corner, and insert this field in that top 2 by 2 corner, and you get an SUN. You're embedding SU2 into SUN, and you embed an SU2 instanton into SUN. Then, if you want, you can do an arbitrary SUN gauge transformation, which gives you something which is a SUN matrix, non-trivial SUN matrix, and that will have a unit topological charge, obviously. So the density of these instantons, as we saw yesterday, is given by this for an SUN, 8 pi squared over g squared for the action. This is the classical density. There's a 1 over g to the 4. If you're into this comes from the various zero modes, translation, rotations, and so on, and rotations within the group, SUN group. There's a volume factor. There's a 1 over to the 4th because you can place the instanton. It effectively takes up a size rho to the 4th, so you have that as a scale. And here's an invariant, a scale invariant measure. So the density at one loop, if you do quantum fluctuations, this becomes a running coupling, clearly, as we well know. And if you make n large, then you know that you should keep the 't Hooft coupling constant. So you put a factor of n here, which means you have a factor of n in the numerator as well, which becomes a power. So this is the old Witten argument that instantons disappear at large n, at least ones where you can use this expression. So you have this G also provides you some 't Hooft coupling to a power of n, because this volume factor here turns this coupling into a 't Hooft coupling. That was this calculation can be found in the old paper in the late 70s by, for example, by Koplik and Lusinov. So small instantons where this formula is certainly valid, and where lambda will be small, lambda rho will be small, so that this factor here is small, taken to the power of n, that will certainly small instantons. The question is, do you use larger instantons? Well, that's more complicated, and there's plausible arguments that you don't. First of all, you can ask yourself whether this factor here is always less than 1 for arbitrary rho. So this is also a function of rho, and you can maximize it. We know this constant at one loop. That's from this paper by Koplik and so on. And what you find is that the maximum value of this is around 3/4. So it is less than 1. And so for all that, it looks like this expression for all values of lambda would disappear at large n. However, at larger rho, the instantons begin to overlap. And of course, this formula may no longer be valid, but in the same way as it's written here. But anyway, as they overlap, they will change the effective action of the instanton. And this was looked at rather carefully in the papers in the late 70s by Calendash and Gross. And their estimate was that for overlapping instantons, this 8 pi squared effectively becomes something closer to 6 pi squared. And if that's the case, then this factor here has a maximum which is bigger than 1. So then you have it will survive the large n limit. So actually, I'm not saying that the Calendash and Gross, I don't think they would say that they're necessarily correct, but it does show that it's quite plausible that larger instantons survive the larger limit, even if small instantons vanish exponentially. Okay, let's move on to something else about continuum instantons and continuum topology, which is very interesting. This, of course, is the theta term, theta vacua. And this goes back again to some comments by Witten a long time ago, more recently, if you like, in the late 90s rather than the late 70s. So this is, you can, of course, the topological charge density, it has dimension 4, just like the usual action. It's a perfectly good renormalizable piece of the action to use. And of course, if you integrate by writing it this way with this factor of 16 pi squared, what I've got here is actually e to the I theta times the topological charge. The charge is an integer, which automatically means that this piece here will be periodic in theta going to theta plus in 2 pi. That is to say, if you have 2 pi here times an integer, you will have it'll be back to itself. So the energy is periodic in 2 pi. And this is an argument that will be true for all n. However, on the other hand, as was pointed out by Massimo yesterday, if you see that actually the energy of any state should be a function of theta over n, just as it is a function not of just g squared, but of g squared n. So how do you deal with that? Witten suggested that the way to deal with that apparent inconsistency, that on the one hand, you should have periodicity in 2 pi, and on the other hand, it should be in 2 pi n, because that's what this would imply, that the periodicity is actually in 2 pi n, not in 2 pi, not necessarily in 2 pi. How do you deal with that? Well, the suggestion is a multi-branch function, where you have effectively, so here is a picture, say SU10, where this is one branch, and it's got a periodicity of 2 pi times 10, 2 pi n, which is 20 pi. But there are a lot of other 2 pi periodicity, because the true vacuum will always be, as Massimo drew yesterday, you go up here, you start, is the ground state, so you go up to here, and then you flip to this one, and then you flip to this one, so you have this kind of a shaped true vacuum. So this is the resolution from Witten. And indeed, it's kind of interesting. The suggestion originally by people like Schiffman, also by looking at n equals 1 SUSY, is that these vacua really are very almost stable. So that if you look at, say, if I looked at SU10, it should be possible to have, they're metastable, but they're pretty stable. There's a very small probability for decay. And that would imply, you know, if you're doing a Monte Carlo, it would imply that you could, in principle, find yourself in one of these vacua, and the physics would be somewhat different from the physics in the true vacuum, the absolute vacuum. I tried to find myself, I tried to find some way of finding myself in this vacuum just very naively a long time ago, and didn't get anywhere. But I still think it will be interesting to see whether one can do that. Anyway, to move on, let's move on to the lattice now. So, as you know, you can do a very easy, naive discretization of the topological charge. So you use the fact that the plaquette on smooth fields is related to the field strength, so that if I simply take the same expression with an epsilon and orthogonal plaquettes, and the one will disappear because of the epsilon, and the linear terms will disappear, and I will get a to the 4th from this product, and the topological charge density on smooth fields. However, once we are considering the rough fields that have fluctuations in all length scales, the ones that you produce, the real world ones, the ones that you produce also on the lattice, since Q, this is not a topological quantity, it's not protected from local fluctuations. These are inverse powers of beta. So the fluctuation in this quantity will be inverse powers of beta. The physical quantity you're interested in is order 8 to the 4th, which is exponentially small in beta, decretum. So the fluctuations will swamp the physical piece. And indeed, this swamping effect is enhanced by the fact that in addition to the fluctuations around this value, there's also a renormalization factor for this, which is traditionally called Z of beta, typical renormalization factor, which at one loop, it's been calculated, that was essentially the people in the late 80s in Pisa, Di Giacomo and his who actually established these pieces of the calculation. So there's a one loop piece like that in SU3, and they gave a formula for SUN. And what you see here is that in SU3, you're typically around beta of 6. And that means that your Z is close to 0. So in actual fact, this factor here almost completely suppresses the physical topological charge you're interested in. So you're looking for a very small quantity with fluctuations, which is difficult and doesn't work very well. So in addition, I should mention that in a rough fields, you need to, when you're putting this on the lattice, these are all forward going, so they don't actually have the symmetry properties, backward forward symmetries of the continuum topological charge, and you have to impose that as well by allowing the mu nu rho sigma to be negative. That's the negative going plaquettes, which is essentially a Clover definition here, a sum of 4 plaquettes, both negative and positive plaquettes. On a rough field. On a smooth field, you can use this, just this, it will work perfectly well. So what is the practical strategy then? The practical strategy is typically to smoothen the lattice gauge field in such a way that you get rid of the high frequency modes that give you all these fluctuations here, and you while preserving the long distance modes, especially because the smoothening, the topological charge is after all something that under local transformations should be essentially unchanged, because in the continuum, after all, the topology of the gauge field cannot be changed by local deformation of the field. So there are various methods, cooling, gradient flow. I'll say a bit more about that later. Here, what I shall normally use is cooling, which means that you take the original gauge field and you do you sweep through that just as if you were with a heat bath, updating it with a heat bath, but instead of using a heat bath, you replace the links in such ways to minimize or reduce the local action density, which is easy enough to do. It's almost like taking the beta to infinity limit of the heat bath. So that you can do for a few sweeps, and very quickly it works, as I'll now show, as you will well know. Well, if before doing that, let me just mention about putting an instant on a lattice, because that can be useful. You can easily do that. Take the field that I gave you, the continuum field, and you can form a corresponding lattice field. The fields on the link matrices just exponentiate the gauge potential along the direction, along the link, the path provided by the link from x to x plus a mu hat direction. You can do that numerically by dividing this path into sections and exponentiate at the end of each section using this well-known formula for SU2. And then at the end of the day, you've got an instanton which is not periodic, because this thing is not periodic. But then you can make it periodic by doing this gauge transformation, G dagger of X, on this lattice field, so that near the boundary, it's almost a unit matrix. The link matrices are nearly unit. And then they won't be exactly unitary because the fields are falling there, but a unit, but you can smoothen the boundary with a few cooling sweeps if you wish. And as I said earlier, for an SUN instanton, you just take the n by n unit matrix and replace the top left-hand 2x2 submatrix by this SU2 field that you've got. So here is a profile of such an instanton, or the 40 to the 4 lattice. I've given it 8 lattice spacings. The rho is 8 lattice spacings, the width. And the solid, so this is summing up, since I can't draw for you the 4-dimensional object, which it really is, I've summed up, I give you a one-dimensional profile where I've summed up over the other 3 dimensions. So this is a section at given times, Euclidean times, and summing up the topological charge density over the other 3 coordinates. And you see this nice peak here, as you inevitably would have with an instanton for this topological charge density, a function of this time. And the solid points are the original things, and you can see there's a slight there is a slight glitch here. The topological charge does jump slightly at the boundary. However, if you do a few smoothing field sweeps, you get rid of that, the open points, and they don't really change very much here. So you can start off with putting topological charges quite easily onto a lattice, if you wish to, in this way. Okay, so calculating the topology of a Monte Carlo rough lattice gauge field. As I remarked, there are number of methods. Cooling is the one I've just mentioned and showed you at least one example, where you replace a heat bath, you sweep through the lattice, replacing heat bath by action minimization or action reduction. There are variations of this in the literature. There's some nice, for example, a very nice bit by Pierre Van Baal in the late 90s, which was a variation where you actually can actually find saddle points as well as minima of the action, which can be useful, obviously, if you're thinking of phaleron or whatever. So an alternative, more recent method is gradient flow, which is it's smoothing as well. It acts in this context. It acts like a smoothing procedure. It starts out in the continuum, and as Martin showed, it's essentially a normalization group invariant. So you can, so the actual time that the number of smoothing sweeps, if you like, but it's really a time that you're doing an equation there with a time variation, a fake time variation, of course. But that is has a invariant meaning, which is quite nice. But it's and then, of course, a very nice way is to use zero modes, for instance, of the Neuberger overlap Dirac operator. You can use that on pure gauge theories, obviously. You can just put it in, and that'll tell you from the number of zero modes what is the topological charge. Or if you're using some other if you're using some other Dirac operator, if you're, of course, in a way, this is ideal if you're doing calculations with fermions. The ideal way to calculate the topological charge is really to use the zero modes or the near zero modes with other Dirac operators to determine what is the topology, because after all, the way that the topology affects your physics is through the Dirac operator. So that's the interesting way for you to calculate, well, as was discussed by Constantia yesterday. But I'm sticking to pure gauge theories, and although one could use these, and they have been used in the past, that's an expensive method which I won't use. So we do know from various work that cooling and gradient flow lead to the same results. There are a number of papers on that, probably more papers, but that's certainly some papers on that. And also that cooling and the Dirac spectral methods lead to essentially the same results. So here I will use cooling, and here's an example of what happens with cooling. So suppose we take some SU8 lattice fields on, happens to be a 20 cube 30 lattice at this value of the string tension, which we calculate simultaneously. And suppose you do 2 cooling sweeps, and you plot the number of fields with different values of the lattice topological charge. And that is these open points. And as you can see, even after 2 cooling sweeps, your fields already fall into clear groups which are quite close to the integer values. If you do 20 cooling sweeps, then you get these solid points, which essentially all the fields, this is a number of fields here, are on the integer, very close to the integer values. So okay, so you may also ask, well, so is it really the case that all these fields that look as if they belong to Q equals 1 actually are the same as the fields here after 20 cooling sweeps. So you can take all the fields. This is an example where you take all the fields that have after 20 cooling sweeps have 0, 1, or 2, topological charge 0, 1, or 2, and you can then look at what is the charge of those fields after 2 cooling sweeps. And here is the plot. So if you take all the fields that after 20 cooling sweeps have 0 charge, after 2 cooling sweeps, this is where they were. Indeed, they were in this bunch here. Those which were around 1 cooling sweep are around here. The others are here. Now, SU8 is a particularly clean example. Maybe that's why I chose it. But you find something similar if you go to SU5, where there's much more, it's less clean in the sense that there's now a little bit of overlap between these things, between these groups here. And the peak, even after 20 cooling sweeps, is not quite as sharp and distinct, but it is clearly extremely sharp and distinct. So there's a minimal amount of ambiguity here. I think this shows that what you see after 20 cooling sweeps is essentially what you had after 2 cooling sweeps. And I think most of us would believe that after 2 cooling, what you see after 2 cooling sweeps, twice through the lattice, cannot be different from what was in the original field, even if the original field is obscured by a lot more fluctuations. So if you use cooling, then you can calculate, as people have in the past many times, that, so this is just our calculation from our papers in SU3 of the topological susceptibility, because we also calculate the string tension and other quantities like global masses. We like to express everything in terms of this physical quantity, the string tension, rather than, for example, in terms of the gradient flow time or the or even R naught, which is another physical quantity, but a bit more. Well, we just don't calculate it, so we don't use that. We use the string tension. And if you do that, here you have for SU3 how the topological susceptibility varies against the lattice spacing. So these are quite coarse lattice spacings. And then we go up to here, and this is by this time we're 6.5, 6.6, 6.7. At this point, we're really losing ergodicity in the topology. There's not so much change in topology, so we ignore this in the fit. But we fit these points, and we get this value for the topological susceptibility. And we can transform that by 2 steps into an MEV value. Now, of course, the pure gauge theory is not a physical theory, is not the physical QCD. So when I say MEV, I'm doing what most people do, which is to ignore that. And so this is really MEV in inverted commas. But anyway, what you can do is you can first go to R naught. So we take the alpha collaborations R naught values in the pure gauge theory and compare them to our string tension values, do a fit, and we find in the continuum that R naught times the square root of string tension has this value, 1.16. And then we take from Rainer Sommer's talk in a few years ago, where he had his best estimate from various sources of R naught in Fermi units. And we use that, combine these two and this to give us 206 MeV as our value for the susceptibility. This is quite consistent with what other accurate calculations have been getting. And so this is not in any sense breaking new ground, but I'm just showing that to you. Also, I'm showing this to you because it's interesting to compare this with, as Constantia yesterday emphasized, in the theory of fermions, the same type of calculation gives you something that varies rapidly with A squared sigma. There's large A squared sigma corrections, large order A squared corrections. But in the pure gauge theories, you can see the order A squared corrections are very small. Even if you plot as she did, chi over sigma squared, I guess, effectively, it was in terms of other R naught to the fourth. This would make it look a bit steeper, but not very steep. The slope is almost consistent with 0. The dashed line is a higher order fit, give you an A to the fourth sigma squared term as well to include these points. As you can see, the continuum limit is within errors the same. So, so that is SU3. If we go now to SUN, we can do the same thing So this was SU2. This is the SU3 calculation I've just shown you. SU4, SU5, SU6. In SU6, we begin to hit the problem of topological freezing. For the smallest lattice spacings, the topology doesn't change anymore within our statistics. So we can't use the smallest lattice spacing, but we do have several lattice spacings where the topology is still changing, and that allows us to do a continuum extrapolation, which is this value. And as you can see, you can do a nice fit with just an order 1 over n squared correction to the topological susceptibility. Again, we calculate the string tension in each case, so that's why I express it in units of the string tension. Well, there are two sets of points here. That's the open points are, well, so far what I've been showing you is where I take the topological charge after 20 cooling sweeps, and it's unambiguous which charge it corresponds to. So rather than using the actual charge, which may be something like 0.97 or something, I make it an integer. That's the solid point. If I took the raw topological charge instead, the non-integer value, I would get these open points. But as again, you can see that while they differ essentially within errors, almost within errors with the other value, so each one of these is a continuum extrapolation here. In the n equals infinity limit, they come to pretty much the same value, and indeed mostly they're within the same value. So we're not introducing any uncertainty by this procedure, I think. So this is the value here for topological susceptibility at n equals infinity. If you take the ratio of this to this and rescale the 206 MeV, you get just over 178 MeV with an error of about 2 or 3 MeV. So it's consistent with this value that Massimo emphasized yesterday that you get from the Witten and Veneziano sum rule, which relates this quantity, the susceptibility, it relates it to the masses of the pseudo Nahm-Goldstein bosons, and eta prime mass. It relates those masses to the susceptibility, and the susceptibility you expect is therefore about 180 MeV, and indeed one finds within small errors, as I say, 178 point something, plus or minus 3, which is consistent with that. So that's quite nice. I mean, but as I say, these are calculations that Massimo showed you some other calculations which came with essentially the same conclusion. So the next thing I would like to mention, and this has to do with the theta vacua, is to do with the topological charge on the original Monte Carlo generated configurations when you calculate it, and its relation to the true topological charge, which I take to be given by the value after 20 cooling sweeps. One could take 10 cooling sweeps, you get exactly the same value even after 5 cooling sweeps. Anyway, so this factor, calculating this factor here, normalization factor. So if you're on SU3, and we have quite high statistics, sort of 20,000 values of configurations on which we calculate the topological charge, so, or more than that even, maybe 100,000 in some cases. So we can, although on an individual lattice field, this quantity seems totally unrelated to the true topological charge, when you average over tens of thousands of fields which have the same topological charge, for example, 3 after cooling, you find that you get values which, while they have significant errors, as you can see here, are very much do follow the linear behavior. That is to say, they're proportional to the true topological charge. And from the slope, you can the slope is given by this factor, renormalization factor. So you can read off the renormalization factor. And indeed, then you can do this for various betas. This was for beta of 6.5 in SU3 on not a very large lattice, but large enough for this purpose. And then you can do that at various other beta values. Here, as you can see, going up to 6.7 from rather coarse lattice spacings. And this is what you find. The dashed line here is the one loop formula that I showed you earlier. So as you can see, the one loop formula doesn't work very well. But that isn't surprising, because if you remember, the correction, the one loop correction was something like 5.5 over beta, which is very close to 1, which means that the higher order corrections are presumably quite large, are large too. So they can't be ignored. So it's not surprising that in this range of beta, the one loop formula isn't working very well. In fact, you might say it's surprising it's working so close to the real values. So instead, what we did in order to provide something useful for other people, we interpolate this with some function, which is quadratic in g squared n in the Hooft coupling. And we provide the interpolating formula that people might wish to use. So here is an interpolating formula of this form for various SUN gauge theories with the range of beta in which we do the interpolation and the values of these coefficients. Now, this is useful. What is it useful for? Well, if you're doing calculations of theta non-zero, then, as has been pointed out by other people, your factor ETI theta q is related to the value that you would calculate on the hot configuration and the value which, after all, you're using when you're updating, for instance, with imaginary theta, when you're updating doing the Monte Carlo, you need to put in this factor here because the q is related to the hot value by the inverse of z of beta. So there it can be, if one wishes, people who wish to use it can use these interpolating things if they fall more or less into this range of betas or equivalent betas if they use, or equivalent values of beta if they're using slightly different action. The thing is that these are interpolating formula, and what we have here is not the one loop value. At asymptotically large beta, this should become the one loop value, and here would be the two loop value and so on. But so these are interpolating formula which shouldn't be used for extrapolation outside this region, or at least not far outside this region. They'll be okay close to that region, but not if you go well outside. But then, so this, I'm just providing this as something that might be useful. Okay, let me move now on to the freezing of topology as lattice spacing goes to 0 and goes to infinity. So this is something that naturally happens. We should remember that in the continuum limit, after all, you can't deform smoothly, you can't deform a field from one topological charge to a different topological charge by local deformations. So by smooth deformations. So we also expect that the Monte Carlo will stop doing that for us as we approach the continuum limit. But one can see by looking at the details that it actually does it very rapidly. So, you know, it's something that happens very rapidly. It's much more rapidly than the critical slowing down of various other quantities, like Lagrange masses and so on, correlations and so on. And the reason for it is actually quite simple, so and well known. So this is the expression for the density of instances of size rho we had. And if you use the one loop formula, you get this expression here. By putting, remember, g at one loop, g squared of rho is 1 over a logarithm, so the exponential of that will give you a power. And if you put in the right factors, you'll get this. Now, what does this tell you? Well, this is really for small instantons, because we're using a one loop formula here for g squared of rho. So it should only be used for small instantons. Now, and it's also telling us that when the instantons are on order size scale, which is a few times the lattice spacing or close to the lattice spacing, they are suppressed by a factor like this, a to the power of 11n over 3 minus 5. So n is 3, this is already a to the 6. And if it's n is higher, then it rapidly becomes a very large power suppression. Now, so if we now go back to asking, when does the topological charge change on a lattice? There are a lot of other fluctuations where there are, of course, many fluctuations where instant and anti-instant pairs can appear just out of fluctuation. So that's not an issue. They can be large and so on. However, if you want to change the topological charge, you've got to shrink a topological charge out through the lattice. What you do is you have a topological charge, which is originally on the size scale of whatever it is, half a Fermi, but it so happens that it becomes smaller, and then it shrinks gradually, and then eventually it shrinks through a hypercube. Once it's within a hypercube, the fields around it become effectively pure gauge, and it just looks like a gauge singularity. It's disappeared. And in the process of doing that, it's a dislocation. But before doing that, it's got to be a very small instanton. And so we can ask, what is the probability of finding very small instantons? That provides an upper bound on the probability of changing topological charge, because any change in topological charge requires the existence of fields which contain an instanton which is almost one lattice spacing across. And that is given by this. So we know that this is at least one suppression factor that's there. There may be extra suppression, there no doubt are extra suppression factors. There's the, depends on your lattice action, what's the probability once you have a small instanton of actually disappearing through the hypercube. So there are other factors that may be there, but this should certainly be there. So this provides, you can see two features of this. One is that if I'm at fixed n, this disappears and I make lattice spacing small, then I get the probability of changing the topological charge should decrease as a power of the lattice spacing, high power of the lattice spacing, depending on n. And if I am at a fixed lattice spacing, but I increase n, then I have an exponential suppression, because of this form here. So what I'll show you is the average number of sweeps when you between changes of the topological charge, just taken from our calculation. And I don't really need this. This is just to show you that there is a freezing. So this is an SU8, 50,000 sweeps. If I start with a field which is topological charge 1, it remains topological charge 1. These are the solid points you get after 20 cooling sweeps. After 2 cooling sweeps, you get these values. If I start with topological charge 2, it remains fixed at over this 50,000 sweeps. In fact, it will remain fixed over 500,000, even 5 million sweeps at this value of beta. But anyway, that's just to, it's not just to illustrate the freezing. Anyway, let's go back to here. The topological charge here so this is the average number of sweeps between changes in the topological charge by 1 unit. And so here what I've taken is 2 sets of calculations for different n, in this case 3, 4, 5, 6, where the lattice spacing is almost the same in units of the string tension. So these points, these calculations all have the same lattice spacing. These have a larger lattice spacing here, but again, within these 3, they have the same lattice spacing. So here I have between 3 and 6. And as you can see, on a log plot, they fall on straight lines, which is saying that these are exponentials. And as you go to larger n, you get, well, so this is here the average distance in SU6 on this particular lattice, with lattice spacing 0.15, it takes about e to the power of 14 is the number of sweeps between changes. At a coarser lattice spacing, the changes are more frequent, and I can go to higher n. We went up to SU12 in that case. We could do this is a very coarse lattice spacing. In fact, it's our coarsest lattice spacing. In fact, it's so coarse that if you go to smaller n, the changes in topological charge are so frequent that we can't really estimate this, because we only calculated the topological charge every 25 or 50 sweeps. And once torque Q is less than 50 sweeps, we don't know how many changes there were. So we can only look at SU8, SU10, SU12 here. Nonetheless, this provides nice, it's consistent with this exponential behavior. And here is what happens if you look at fixed n for different, going from SU3 to SU8, SU3 here, SU8 here, so increasing n. And you look at what happens when you vary A, the lattice spacing, and you've normalized things to a common volume in terms of the string tension. Then here you see power law. So log plot. So these are power laws, and this is consistent with a sort of power law behavior. So this follows, roughly speaking, those expectations. I should emphasize that I don't think the accuracy is the functional form. It's consistent with these functional forms, but it's perfectly plausible that the functional form, other functional forms might also fit. You know, you have 3 points here. You could probably fit this with other functional forms, but it's consistent. It's pretty impressive that it's quite consistent across all these values with this kind of power law functional form. So that's a topological freezing. Now, the question is, does it matter, the topological freezing? Well, first of all, at large n, for the kind of calculations we were doing, which is glue ball, string tension, and so on, it should not matter precisely because of Witten's interlaced theta vacua. So if we are in this near this we are in this particular theta vacuum, which has periodicity of 2 pi n. So near theta equals 0, it's extremely flat as n becomes large. So extremely flat effectively means that if you look at the correlator of some glue ball correlator with q squared, its effect, the connected piece is order 1 over n squared. So it goes to 0. So in other words, the correlation between q and the correlator disappears as you go to large n because of the interlaced theta, because of this 2 pi n periodicity of the individual vacuum on which you're sitting at theta equals 0. So that's so you expect that for large n, it really you shouldn't see much effect from topological freezing because the theta dependence effectively goes to, it becomes trivial in the neighborhood of theta equals 0 at large n. If you are not at, well, moderate n, then you find that at least in our range of lattice spacings, it doesn't affect us certainly up to SU5 and most of SU6. The smallest lattice spacing is affected. So then we also in SU8, where you do have for n larger than 8, you do have topological freezing, although we expect on theoretical grounds here that it shouldn't affect the glue ball spectrum. We did check doing a high statistics calculation where we used configurations which had just had 0 topological charge and compared them with using configurations with various non-zero topological charges. Obtaining non-zero topological charges was done by starting with fields which have non-zero topological charge, a whole range of fields with non-zero topological charge, a reasonable range. And by comparing the two sets, we saw that we had no visible effect on any of the glue balls in any of the irreducible representations you have on the lattice rotational group. So parity or charge conjugation, no visible effect within errors. So this already gives quite strong evidence that we shouldn't be too concerned about topological freezing in the calculations we're doing. And we try to sort of improve things a little bit because for where we did have topological freezing, what we did is we started with a range of configurations running in parallel, which had a distribution of topological charge, which was more or less what we expected from either from lower n, smaller n, where we could actually calculate the distribution from our Monte Carlo, or from a very crude large lattice spacings at the same n, like SU8, at larger lattice spacings where you could still have topological charge changing, and you could see what the distribution was. So by putting in we put in a distribution, and we think that sort of was an extra piece to which I think is useful. Whether it was necessary is probably not necessary, but it was useful to as a further check on things. And now the problem, of course, for glue balls and string tensions is fine, but if you're actually interested what happens at large n to topology, this is of course not so useful, this whole business, because you're not seeing changes in topology. If, for example, you want to look at the like Massimo did at the distribution of the topological charge, he was looking at high temperature, but if you want to look at that distribution of topological charge to see how it differs from Gaussian, to tell you something about interactions between instantons and so on, you need to produce things with a weight determined by the Monte Carlo, and this does not do that. So those kind of quantities cannot be addressed by this procedure. But if you're interested in things like glue balls and string tensions, I think we've done a lot of checks to show that you don't have to worry about topological freezing if you do some strategy like this. Of course, this is for pure gauge. I mean, once you include fermions, then you have to rethink. So there are other ways. Of course, people have looked at better ways of dealing with freezing in order to actually change topological charge more frequently. One way is, of course, to use extremely large volumes. and look at smaller subvolumes, which are several Fermi across, but still small compared to the total volume. That's obviously computationally expensive. We wouldn't want to use that at present times on our large N calculations. I mean, that seems implausible. People have also used non-periodic boundary conditions, open at one end, so that instantons can drift in and out. I think it's fair to say that the success has been partial. Most recently, there's been a nice development where people have used a defect, originally introduced by Hasenbusch and I think with CPN models, and recently it's been taken over by Bonanno et al. To where you have a defect which you keep things, you make sure that everything follows the right weightings, and but it's computationally expensive, it has to be said. It's very much the calculation they did here, Bonanno et al. Is very much more expensive than anything we did. So it's nice as a check, but at the moment, it's probably going to be difficult in its present form to use in normal situations. So let me just finish with the final comment, is that, of course, changes in the topological charge during the Monte Carlo are themselves a lattice artifact. In the continuum limit, you wouldn't have any changes. That's the nature of the topological charge, topology. However, it is a useful, of course, because it gives us the right weighting of different topological charge sectors, which otherwise we have to think of obtaining in different ways. So that's my final comment on topological freezing. Let me finish now with a few comments about, which is just playing around with some further methods for lattice topology. The motivation here is that, as we've seen, we have many mutually consistent methods for calculating total topological charge of a lattice field. But the topological charge density itself is more tricky. If you smoothen the fields, you're certainly changing it. If I cool, I get a very different topological charge density after 20 cooling sweeps than I do after 2. The total topological charge will not change, but then everything gets shifted around. So the question is, are there some other, so how do we check whether we are, will 2 or 3 or 4 cooling sweeps not change the topological charge density significantly? Can I use that? How do I check whether I can use that? So it's really a question of calculating the physical density. And so one method that I would like to emphasize here in the last few minutes, emphasize only because I've been playing around with it recently, and it's in this paper, up here, is something which I call repetition. And then also I looked at blocking and smearing, and these methods were really something that were, including repetition, were mentioned in a paper long ago. But then the interest in topology disappeared in the lattice community for a few years, so I never followed it up. I thought why not follow it up now? The interest in the topology in the lattice community has come in waves over time. And we are obviously good reasons in a particular wave now, for reasons to do with fermions above all. Anyway, so there was, so let me talk about repetition. So what is the idea here? It's a very naive idea. So you've got a given field, which I will call the link matrices, and I'll label it by 0. It's a given field you've got, which a Monte Carlo has produced. It's got fluctuations. And you would like to know what is, you would like to average out those fluctuations somehow while being sure that you really haven't done anything to the long distance fluctuations of the fields. So one way, what you know from your Monte Carlo experience is that if you do 1, 2, or 3 Monte Carlo steps and the lattice spacing is small, you will change the high frequency modes, but you won't change the long distance modes. So the idea is to produce a whole ensemble of fields that are just 3 Monte Carlos, for example, 3 Monte Carlo sweeps away from this original field. And I'll show you some results where the ensemble has 10,000 members. So I have 10,000 fields which are related to the original field by 3 Monte Carlo sweeps. And the only difference is that I used different random numbers in generating these 3 Monte Carlo sweeps. So they're different. So, and then on this ensemble, I calculate averages. I average quantities like the topological charge density. And I would expect that the topological charge density I get after averaging over after only 3 Monte Carlo sweeps would be a very good representation of what there was, the long distance modes in the original field. Of course, the question is whether you can do that with a reasonable number of size ensemble. I've mentioned 10,000. Can you do it with 10,000, or do you really need 1 million for it to work? As it turns out, 10,000 does work quite well. So let me show you some results for that. First of all, I don't show you the density, I just show you the average topological charge. So I've taken 5, in SU3, I've generated 5 fields with different topological charges. These are topological charges that you find after 20 pooling sweeps. So I've got these 5 different fields, which were originally generated at 6.235 on this lattice. And then I do an ensemble of fields that are 10,000 fields that are 3 sweeps away from this one, a different ensemble 3 sweeps away from this one, and so on. And I look at the average topological charge on those fields. So here is the value of the topological charge I obtain after 20 pooling sweeps. And here is the average value. And as you can see, you have very small errors on total topological charge. So it has wiped out the high frequency fluctuations quite effectively here. And indeed, if I look at this slope here, it is consistent with the slope that I obtained before as being the Z of beta, which is what you would expect. After all, you are using normal Monte Carlo steps away from that. So those fields. So it does seem to, at least, but the point I want to emphasize is the errors are quite small. So it looks like you get something with 10,000 fields. So now we look at the topological charge density. For example, for the Q equals 1 minus 1 field. And I take the that one field, and I take an ensemble of 10 to the 4, 10,000 fields, which are 3 heat bath sweeps away from this field. And I plot the profile where so this is like my instanton profile much earlier in this talk, where I sum up over the different other coordinates and plot what's the total topological charge at each Euclidean time space. And you get this. So, and as you can see, it's not that you don't get errors which are large, you get errors which are quite small. And this, I would say, is certainly a very good representation, a decent representation of what were the original long distance fluctuations in that field. And then if you look at, so I'll really finish, I think, here. And if you look at the, for example, if you look at what you get from cooling, I show you what you get after 2 cooling sweeps, renormalizing the total, renormalizing the values so they have the same total topological charge, because remember the ones which are obtained by this iterative method are renormalized by a factor of Z of beta. So I remove that factor. And then you can compare them, and as you can see, they follow very well each other. So this provides what I see, this method of iteration, this repetition, finding these ensembles, it's rather expensive, but what it does do is enable us to check other methods. And here, what this would say is that at this value of beta in SU3, doing 2 cooling sweeps gives you a pretty good representation of the topological charge density in the original field. If I took, say, 15 cooling sweeps, I would get something quite different from the values that I obtained by repetition, and that wouldn't be a good representation anymore. So that's a way of checking things. So that would, well, I'm running out of time, so I'll stop there. I won't say anything about blocking and smearing. Both techniques have their positive points, and I would refer to the paper that I originally gave earlier this year, in February this year, to see a discussion on that. But my main conclusions, if you like, are that the topological charge is under a good total topological charge. We can calculate very accurately. We can calculate it at large n. We get values that are consistent with the Witten-Veneziano formula. We understand why the argument about large n instantons disappearing doesn't apply really as soon as you consider larger instantons. And we can understand topological freezing, and we have we can also check where it's important, where it isn't. And for global string tension calculations, it's clearly not important. And we have a sort of strategy for improving things a bit there. And there are other methods which are interesting, which have recently been developed, which one would like to see pursued further. And then there is this final thing about a few ideas, including this production of these ensembles, which are just removed by 3 sweeps or 2 sweeps from the original Monte Carlo field. And we can see how that helps us to check other methods as well when we're interested in topological charge density. Okay, I'll stop there. And if there are any questions, I'd be happy to address them.
So thank you, Mike. So questions? Maybe we have time for 1, 2 questions. Yep, yeah.
So maybe a basic question. So the fact that we have topological quantization on toroidal backgrounds with periodic boundary conditions. I mean, I found a proof of this, or claimed proof, in the paper by Leutwiler and Smilger, but what would be a canonical reference for that, or is there also like an easy way to see that?
Okay, I wasn't sure. One of the things that a finite volume does, one should bear in mind, is it breaks scale invariance, classical scale invariance. So actually your instanton is no longer classically scale invariant, or your approximate instanton, it's not scale invariance. One should bear that in mind. And that's not just a lattice effect, that's a continuum effect. I'm not quite answering your question immediately, partly because I should say that I'm not sure if I can offhand give you a good reference. However, the breaking of scale invariance is extremely small compared to the breaking of scale invariance from quantum fluctuation. So in practice, we just ignore it. So everything I discussed here was on the basis of quantum fluctuations being the only factor that's relevant. But actually, a finite volume does make a difference. And and of course, there are other complete interesting things, such as that if your volume, when we normally talk of periodic boundary conditions, we mean periodic boundary conditions on the gauge potentials. However, if you're talking about periodic boundary conditions on gauge invariant quantities, trace f mu nu squared, then of course you will include fields which have what they call twisted boundary conditions. So this is different from the twisted masses that you use. This is actually in the pure gauge theory. It's to do with the center, using the center symmetry on the boundary, on the gauge transformation around the boundary, which is belongs to the center symmetry and therefore is invisible to gauge invariant quantities, at least local gauge invariant quantities. And it's there you can actually have fractional topological charges. And this has been something that's been pursued a great deal over the years by Tony Gonzalez Arroyo and Maria Garcia Perez in Madrid. So that's interesting. You can have topological charges. And this is due to the fact that these boundary conditions introduce chromoelectric and chromomagnetic fields across the lattice, which can give you a sort of E dot B factor, which is actually has a non-zero topological charge, but these fields are quantized, and so it's still a quantization, but it's a quantization, I think, well, anyway, the references there would be papers by Gonzalez Arroyo. But yeah, so I don't have I don't have a perfect I don't have an answer for my understanding. Well, originally that is that there are proofs for a spherical geometry. So if you're on a sphere, not a torus, 4-dimensional sphere, but not a torus, that is to say, on a 4-dimensional sphere, all the points at infinity go to one point, while a torus is somewhat obviously different. Hypertorus is different. So I'm not sure about that. Actually, that's an interesting question. I'll chase it up for myself, actually, but I can't answer it here. What is it?
Please let me know in case you find anything.
Yeah, okay. Okay, yeah.
Thank you.
Okay, thanks for the question.
Maybe one more question, we go for a coffee break. So since there are no more questions, let's thank Mike again.
Thank you very much. Thanks.